Welcome to this explainer. We're diving into a complete masterclass on coordinate geometry today. My goal here is to walk you through a comprehensive teaching script straight from our source lectures. We're not skipping a single topic, definition, formula, or shortcut. We're going to cover absolutely everything, right in order, so you leave with complete mastery.
Here is our roadmap for today. We'll start with an introduction, move through the Cartesian system, define abscissa and ordinate, tackle some point location practice, explore mirror images, and finish up with a final capstone checklist. Let's get right to it.
Section 1. Introduction to Coordinate Geometry.
So, what actually is coordinate geometry? Simply put, it's the branch of mathematics that lets us describe geometry using coordinate points. And we really have to give a huge shout out to René Descartes here. He's known as the father of analytical geometry. The guy literally gave us the mathematical tools to translate physical, real-world shapes into numbers. Pretty wild, right?
And if you're wondering, okay, but why does this matter to me? Just look around. This is the exact engine running your world. From the GPS tracking your phone right now, to satellite imagery, maps, and calculating distances in physics, these coordinate points map our entire physical reality. Whether you're tracking an airplane or just trying to find the nearest coffee shop, coordinate geometry is doing the heavy lifting behind the scenes.
Section 2. The Cartesian System. Okay, to build these maps, we need a structural foundation, and that is the Cartesian system. Imagine a 2D plane split into 4 distinct quadrants. Here's the cheat sheet you'll want to memorize. Quadrant I is positive, positive. Quadrant 2 is negative, positive. Quadrant 3 is perfectly negative, negative. And quadrant 4 is positive, negative. Plus, we have strict axis rules. Any point sitting anywhere on the x-axis, its y-coordinate is strictly 0, period. And the exact reverse is true for the y-axis. Any point there has an x-coordinate of 0.
Section 3. Coordinates, abscissa, and ordinate.
Let's talk terminology. When mathematicians look at an ordered pair, like x, y, they use some specific fancy names, but it's actually super simple to remember. The horizontal x-coordinate is called the abscissa, and the vertical y-coordinate is called the ordinate. Put them together, and you've got your coordinates.
Section 4. Point location practice questions. Let's put these definitions to work.
Time for a quick quadrant logic test. Take a point like -3, 5. It has a negative abscissa and a positive ordinate, so boom, it sits right in the second quadrant. Actually, any point with a negative x and positive y lives there. What if both coordinates are negative? That's always quadrant 3. Now, how about a point like 0, -7? Since the x-coordinate is 0, it rests squarely on the y-axis. So if you need to find a point exactly 5 units down in the negative direction of the y-axis, you just write 0, -5. Super straightforward.
Let's zoom in on those axes for a second. The ordinate, which, remember, is just our y-value, of every single point on the x-axis is exactly 0. Meanwhile, the abscissa on that same horizontal axis can be literally any number in the world. So, out of a random set of points, only the ones like 8, 0, or the origin right at 0, 0 actually sit flat on the horizontal line, simply because their y-coordinates are a perfect 0.
Visualizing distance can feel a bit abstract, but think of it this way. If a point's perpendicular distance from the x-axis is exactly 5 units, well, its y-coordinate has to be either 5 or -5, right? It just depends on whether it's floating above or hanging below the axis. Similarly, if you know a point P is sitting down in the 4th quadrant, it's below the x-axis, meaning its ordinate drops to a negative value. Let's call it -b. If you look at a graph and go left 2 and up 4, you're looking right at point P, mapped perfectly as -2, 4.
Let's do some rapid-fire arithmetic with these terms. Say you need to subtract the abscissa of Q from P. If P is at -2, 3, and Q is at -3, 5, you just take -2 minus -3. That gives us a positive 1. Let's try another pair. P at -2, 7, and Q at -5, 9. We just take -2 minus -5, which yields 3. You're really just picking out the x values and running the basic math.
Now this is where it gets really cool. A fantastic geometric application. Imagine an equilateral triangle anchored directly on the y-axis. We can use good old Pythagoras' theorem here. If the base lying along the x-axis is a and the hypotenuse is 2a, we set up our formula. Hypotenuse squared equals perpendicular squared plus base squared. So we solve the equation 4a squared equals a squared plus x squared. Subtract a squared, and we're left with 3a squared equals x squared. Taking the square root reveals our exact intersecting points on the y-axis at plus and minus a root 3. Those are our missing coordinate points, C and D.
To wrap up our point plotting drill, whether you're identifying that 7, 0 and negative 8, 0 lie flat on the x-axis, or you're plotting a whole table full of tricky decimals like 0, negative 1.25, the core strategy is rock solid. Just check the signs. Positive x goes right, negative goes left. Positive y goes up, negative goes down. Master that basic rhythm, and you can map absolutely anything on the grid.
Section 5. Mirror images and reflections.
Okay, I absolutely love this part. This is essentially a cheat code for reflections. We use a really simple mirror image matrix. If you reflect a point across the x-axis, you only change the sign of the y-coordinate. So x comma y becomes x comma negative y. And if you reflect across the y-axis, you only flip the x-coordinate. So x comma y becomes negative x comma y. That is the whole trick.
Let's apply that trick right now. The mirror image of 7, negative 8 across the y-axis, just flip the x. It instantly becomes negative 7, negative 8. And it gets cooler. If you take a point like A at negative 4, 2, and reflect it across the x-axis, then the y-axis, and then straight through the origin, you end up tracing out a perfect geometric rectangle with those 4 points. It's like mathematical magic. You know, we can even run this in reverse algebraically. It's a fun little puzzle. Let's say a point's reflection in the x-axis is given as 5, negative 6. Well, that means its original y must have been positive 6. But since reflecting across the x-axis leaves the x-coordinate untouched, we know our original x expression, let's say it was x plus 3, must equal 5. That means x is simply 2. We can check our work seamlessly. 2 plus 4 is 6, and the mirror of 6 across the x-axis is indeed negative 6. It works out perfectly.
Let's tackle one last geometric puzzle. We want to find the area of a square, and we know 3 of its vertices are at 3, 2, negative 2, 2, and 3, negative 3. Just by plotting those, we can easily find the missing corner at negative 2, negative 3. Now, measuring the horizontal distance from x equals 3 over to x equals negative 2, we get a side length of 5. Square that side length, and boom! Exactly 25 square units.
Section 6. Final review and checklist.
As promised, here is your verifiable capstone checklist to prove we didn't miss a thing from the source material. We nailed the Cartesian system rules, defined abscissa and ordinate, worked through Pythagorean applications, unlocked the reflection matrix, and plotted every single practice question required. You have officially conquered the fundamentals of coordinate geometry. As we wrap up this explainer, I want to leave you with a thought. What invisible mathematical coordinate grids and precise geometric shapes are actively determining the exact route your GPS is guiding you on right now? The next time you pull up a map on your phone, think of René Descartes, remember your abscissa and ordinate, and remember everything from this masterclass. Thanks so much for learning with me today.